Start the recording. Welcome everybody. So this is now the third lecture by Professor David Stern, who is the Francqui chair holder at the University of Hasselt. So as the same as last time, so please ask questions, and you can do that throughout the lecture. And also at the end of the lecture during the discussion, you can just type your question in the chat, or you can raise your hand. There is a raise hand button next to the camera button at the bottom of Blackboard. And then David calls you up and you can directly ask your question. So I would also like to emphasize that there will be two more lectures. One lecture will be on April 23rd about energy and the Industrial Revolution. And then on April 30, we will have a session on econometric modeling of global climate change. So,
okay, thank you.
Sorry, I need to say this GDPR thing now.
Right.
So with respect to GDPR, it's important to mention now that this lecture is recorded and will be later available online. I will post in the chat where it is online. And so with staying with us, you agree that this will happen. Okay, so thank you.
Yeah. Thank you, Stefan. If I don't notice a question somebody asked, for some reason my software is not updating me here, then Stefan, please let me know that somebody asked a question during the lecture. So last week we talked about energy and economic growth, and one of the key points there was a very stable relationship between energy use per capita and GDP per capita across countries and across time. So as countries grew and became richer, they did have a bit of a lower energy intensity, but we didn't see any sort of really significant shift of that relationships down, so that all countries had a lower energy intensity over time, irrespective of their level of development. We didn't see that. So the question is, if there have been very big gains in technology, like we now have LED bulbs that use hardly any electricity, compared to previously we had fluorescent ones which used a bit more to produce light, and before that incandescent bulbs used even more, and before that there were gas lamps and candles. So there's been huge gains in the amount of energy service we can get for a given amount of energy. And that's just one example. Why don't we see a sort of shift down in energy intensity across all levels of development, so that there isn't a stable relationship and the curve is shifting down over time? And so we're going to try and address that question today by talking about the rebound effect, which looks at how energy use responds to improvements in energy efficiency. So that's sort of setting the scene. So going to talk first about what is this rebound effect, and then go on to talk about the economy-wide rebound effect. So we can think about rebound micro level, but also at a macro level. I'm going to then focus on the macro level and talk about what evidence there is to how big the rebound is. And then the third part, I'll talk about our own work to try to empirically estimate this economy-wide rebound. So again, probably starts fairly basic, and not as basic as a couple of the previous lectures, and then gets a bit more technical as it goes on. But yeah, I can keep you with me throughout. So what is the rebound effect? This is just I thought this looked like something bouncing, like bouncing back. It was some PowerPoint suggested it. So what is this rebound effect? So we can start with the most basic, simplest level. And we look at a consumer who's using an energy service in a household. And this might be lighting or heating or cooling, refrigeration, so forth, are examples of energy services. Household, it could be, of course, also driving cars and so forth. And so this household produces this energy service themselves using energy which they buy, though today, of course, they might use energy from a solar panel attached to their own house. and or in developing countries collect the energy. But anyway, they take an energy input, they use other inputs as well to produce this energy service. And we're going to look at what's called the consumption rebound effect, which is the basic idea which we then build on from there. So the household's got a demand curve for this energy service, even if it's not something that's traded on the market, it's something they're actually producing themselves. And then from there, they have a demand for energy, a derived demand for energy. And this is a diagram I came up with to try to explain explain this relationship. So we have here the upper segment or quadrant here, which is half. There's no, actually not four, so it's not a quadrant. The upper area here is this is just simply a demand curve for energy service, and the amount of service is on this x-axis, and then the cost of producing this service is on the y-axis. And initially we have cost on marginal cost 0. That's the current cost of producing another unit of this service. We just assume it's fixed, keep things simple. And then given that demand curve, we would use this amount as 0 of the service. Just the standard demand curve, standard introductory economics. Down here I drew, well, for this level of service and some other assumptions, very simplified, we draw down here. Down here we have instead the amount of service and the amount of energy required to produce that service. So we're kind of assuming all other prices, the price of actually energy on the market and the price of other inputs are constant, so that we don't change the mix of different inputs in any other ways after we have the efficiency improvement. So using S0 the service, this curve tells us how much energy we need to use. We need to use E0 of energy. Axis here, if we're using S0 of the energy service. So it's important to think energy service, not doing something with the energy. We don't really want energy per se. We want the services that it produces. So this is like a schedule relationship that shows how much energy we need for a given amount of service. And this is again zero. Nothing's changed yet with the initial state before there's been any improvement in efficiency. Okay, so this is a diagram I made up. I don't know if it makes sense. People generally found it actually quite useful. Okay, so what happens? There's an innovation, or we adopt an innovation that reduces the amount of energy input we need to produce the energy service. So suddenly fridges are more energy efficient, and we get a new one, or we get LED light bulbs put in our house, or something like this. Nothing else changed. We just adopted energy saving innovation. What happens? Two main things happen. Well, the cost of producing that service is now lower because it requires less energy to produce it. And so we're now at a marginal cost of C1, okay? And this was the demand curve for the energy service. If it's now cheaper to produce it, okay? So what we're not looking at here is where it's costly to save energy, or saving energy requires lots of additional material inputs, like we install insulation, and maybe it costs just as much as the energy that's saved. We're thinking of a pure technological improvement, okay, not sort of substituting materials for energy. In this case, yes, an energy-saving innovation would reduce the cost of providing that service. And then, of course, this is just the demand curve. We're going to demand more of that service, and that is the essence of rebound. And then down here, this was the original relationship between the energy service and the amount of energy we need. The new one here requires less energy per unit of a service. So we now are consuming more of a service, but we're more energy efficient. And so we read off this curve, we now have energy consumption E1R, which is less than the original level E0. So we have saved energy in this example. Okay, by adopting the service, we're better off, we have more energy services, and we're using less energy. where the rebound bit comes in, if we adopted the energy innovation, but we still consumed S0, we didn't consume any more of the service, then we would go point here down to the new energy service relationship and would be consuming E1N, no rebound, okay, less. And the fact that we consume more of a service means our energy uses bounced back a bit from the pure reduction would have happened if we hadn't increased our use of the service. But we're still saving energy. So this example, rebound is not 100% or more than 100%. It's actually quite small in this example. Okay, that's the basic idea. It's called the direct rebound effect, an example of a consumer. Okay. That's the basic idea. We want more energy services that uses more energy than it would if we just stuck with this previous level of energy service. Okay, so yeah, so that just pretty much said what I just said, those slides. Okay, and so it increases it again, or the full adjustment involves a bit of a bounce back in energy use. Okay, so that is the idea. We can define the rebound effect like this. R is 1 minus actual energy savings divided by potential energy savings. So if we'd had a 1% improvement in energy efficiency, but in the end we only save 0.5% of energy, then the rebound is 1 minus half, it's 50%. Okay, if we actually saved as much as the potential, the sort of engineering potential, then the 1 minus 1 would be no rebound at all. So those are a couple of examples of if we didn't save any energy, then the rebound's 100%. So actually, there's not an increase in energy use, just we didn't save any energy. We used so much more of a service, we didn't save any energy after the efficiency improvement. Of course, energy use is not the only input we're using here. If we're thinking about a car, there is gasoline, petrol to drive the car, but there's also a capital cost of the car. Both of those are costs of transport. The same for household appliances. There's a capital cost and there is energy cost. So if the energy required reduces by 1% for the same service, that doesn't reduce total costs by 1%, but only 0.5% if say, for example, the share of energy is half the total cost. So if half the total cost of driving is gasoline, then 1% improvement in the efficiency of the car only reduces the cost of driving by 0.5%. So we need to take that into account. So S is the share of energy in costs of energy service, and then epsilon is the elasticity of the energy service with respect to its price. So so if it's a elasticity of 50% of minus 0.5, then 1% reduction in the price means we consume 0.5% more of the energy service. Okay, so okay, so we need to take both those factors into account to work out the rebound effect. People often forget that and just translates the elasticity immediately into an estimate of the rebound effect. There's so many papers like that out there that don't take into account that energy use is only part of the total costs. So this is actually the change in energy service for a 1% efficiency improvement. And that works out as the rebound effect as well, because minus 1 is, like, say, a 1% reduction potential. This is the change in use of the energy service for that change in efficiency. And so this is the actual, and that's the potential, the full 1%. So that works out to, this is the actual rebound effect. So There's a guy at University of Western Australia. He published a paper. He said, if you don't know what the elasticity of demand is, it's 0.5. And had a lot of evidence why that's the case. So let's assume elasticity of demand is 0.5 and energy costs are half the total costs of producing energy service, then the rebound is 25%. And it turns out actually a lot of estimates of the size of the direct rebound effect for consumers are around about that 25–30% mark. So it's a rough rule of thumb. Assume S is 0.5, assume eta is, epsilon is minus 0.5 seems a good assumption. So the direct rebound effects in consumption are actually quite small. Important, but not dramatic. Those overturn our assumptions about energy efficiency. But that's not the end of the story. So now we're saving energy. We're better off than we were before. Not only do we use more of energy service, but also complementary goods. So if it's now easier to heat your home, okay, maybe you extend your home or buy a bigger one the next time, okay? We see this a lot in car. If our engines are more energy efficient, maybe car manufacturers will provide larger cars, heavier cars, cars that accelerate faster, and both those things have happened. The actual efficiency of internal combustion engines increased a lot more than the fuel economy of cars. They've used quite a lot of that improvement in efficiency to increase other dimensions of the car. And as I said, similarly, complementary goods like houses, and then if you like more rooms, well, you're going to heat more rooms and so forth. So we're going to use more energy services that are complementary to the initial to the good whose efficiency is improved, and then also other goods and services. There's no reason why it would be limited just to other energy services that require energy and production. Okay, so the rebalance, the example of the car is not just you drive more, but you also get other dimensions of the car at change. Maybe that's part of direct rebound in the car, but then it requires more energy to produce larger, heavier cars somewhere else in the economy. So we're demanding other goods and services that either to use energy directly or use energy and then manufacture somewhere else in the economy. So these are indirect consumption rebound effects. Something people often ignore. People talk a lot about this, that people maybe try to save energy and then they spend the extra money going on vacation and flying in a plane and using more energy. But also, of course, substitute goods are reduced. So it's not just, there's a little bit more complicated story than some of the stories you hear about. Yes, people spend on all these energy intensive things with the energy they saved. There'll also be a reduction in demand for the substitute goods if real income has increased. Okay. Thinking about production, there should be rebound effects here too. So innovation reduces required energy per unit's output, everything else held constant. Okay. That means the marginal cost of producing a unit of the good has declined. And so whether you're in perfect competition or got market power, it doesn't matter. Your profit maximizing output will increase as a result. So there's a rebound there. You don't just save energy, you want to increase your output. I first heard about this effect, actually, a paper about improvement by a guy called Roy Darwin, who was about improvements in, what's it called, sawmilling, where tree logs are turned into wood. So efficiency in turning trees into wood resulted in actually more use of wood rather than less. And there's an example from the Pacific Northwest in the US, which is a very interesting paper published several decades ago. So it's not just energy, it's other things as well. You think you're saving a resource, but there is some rebound to that. So yeah, demand for energy rebounds. Now, if the firm is facing very elastic demand, for example, their exporter in a small country facing international demand. Maybe the whole industry in that country has energy efficiency improvement, but faces very elastic demand in exports. There is a bigger potential here for direct rebound than in consumption, where at least in the short run, consumers are limited by their income or their wealth. So how much they can react. A firm, if it has got elastic demand, could expand production a lot. Of course, a single firm has got the biggest potential to expand production, or industries in small countries, and finding big economies is probably a bit less potential for whole economies or whole industries to see rebound on the production side. It might then not be much more than for consumers. This is borne out in the simulation modeling I'll talk about later. Well, that isn't everything. Well, there's, of course, indirect rebound in production. So, yes, as you expand production and use more energy, again, you will also use more capital, which requires energy to be produced somewhere else in the economy and maintained, and more labor and other inputs, raw materials that take energy to mine them or grow them. So that's indirect rebound in production. And we haven't yet talked about prices changing. That's just partial equilibrium. So some papers just compute the partial equilibrium effect, with all prices held constant, apart from the cost of producing the energy service. But the price of energy constant, price of capital constant, wage rates constant, partial equilibrium. But the price is going to change. So this is a paper that laid it out pretty well. By Kenneth Gillingham at Yale University and some co-authors. I forgot, Gurno Wagner, I think, who's a climate economist at New York University. Anyway, they did a survey on the rebound effect and energy efficiency policy, and this is a graph, first graph in the paper, the macroeconomic price effect. So the idea here is demand for energy. Now we're talking about demand for energy in the economy is D. And then there's an efficiency improvement to reduce the demand for energy to D prime. Okay, so we're assuming there's less than 100% rebound initially, and demand for energy does fall, though not by as much as the actual efficiency improvement. So this is supply for energy. They just drew it like in a standard introductory economics textbook, a rising supply of energy. We were at this point here. And if the full efficiency, if there's no further effect here, the energy use change after taking into account those direct and indirect rebounds brings us to this point on the new lower demand curve, and we'll be consuming, instead of A level of energy, we'll be consuming now B level of energy. But because the supply curve is sloping in the way it is, the price of energy falls. And we move down this new supply curve, sorry, this new demand curve, to a new equilibrium point at C. So the supply curve looks like this for energy. Then at the macro level, there's this additional effect of energy getting cheaper and an extra rebound from B back to C. So that's increasing the rebound effect further. Okay. But what if the supply elasticity was different to this one shown in the paper, shown in their paper? Well, so I just redrew their diagram with a totally flat supply curve. This is the infinite elasticity of supply, and that means the price of energy stays constant. We can always produce more energy at the same cost. In the longer run, maybe that's true to some degree, possibly. So in this case, the old equilibrium was here, the new equilibrium is there. There's no additional effect from price of energy falling. The price of energy doesn't fall when the demand for energy falls. The price of energy stays constant, so there's no extra rebound here. On the other hand, if the supply of energy was very inelastic, which, in example, in the short run, you might assume for something like oil or natural gas, okay, or even for electricity, there's a limit on the number of power plants installed. Okay, maybe we can build more or add some more solar panels. In the short run, though, there's an upper bound where supply is relatively inelastic in the short run. what happens here is the demand curve shifts down, and all of the effect is translated to falling energy prices. Okay. There's no, and so instead of an energy saving like this from A to B, there's no energy saving at all. In fact, there's 100% rebound. Okay, irrespective of what the direct and indirect rebounds were in the partial equilibrium case. If the energy supply is fixed here, and then it gets translated totally in a price effect, and we move a long way down the demand curve, not just to here, but all the way down to here. So the elasticity of supply of energy is very, very important for estimating what the rebound is, it turns out. And in the short run, actually, that shows it could be actually larger than in the long run, which is kind of opposite of what people often assume. But yeah, that's a critical factor in working out the rebound, this macroeconomic price effect of energy. So that actually is a general equilibrium. Okay, well, that was the price of energy. So of course the wage rate changes, and the price of capital changes, and materials, everything changes. So then we get finally to a general equilibrium. I'm not going to go into those. There's a paper by Lemoyne that I'll be citing later. It's actually very good, but he does assume that the supply curve of energy looks like that. So he actually ends up with a relatively smaller rebound, but if he assumed it was like that, and certainly if he assumed it was like that one, so he assumes that a priori. So it's not that surprising. His rebound estimate is quite relatively on the smaller side. And then short run versus long run. So in the short run, businesses and consumers are constrained by their current income and installed consumption capital. Businesses are constrained by their existing capital. But we should think about, in sort of thinking about an economic growth model, we should think, like the solo model, we should think about that energy efficiency improvement in productivity, and productivity increase, then we're going to adjust by investing and increasing the capital stock and expanding production. So that limits short run effects. Longer run effects could be a lot bigger from that dimension. On the other hand, the price effect might work in the opposite way and may reduce rebound in the long run. So a lot going on here, and purely from sort of theory, it's hard to say how big this rebound effect really is. And when we take all those facts into account, then we can call that economy-wide rebound. All those factors taken into account in general equilibrium, and also looking at the long-run dimension of the problem. What is the end result? Okay, so I thought this was good, bringing all these little bits together into the full pattern. Okay, so that was the introduction with a bit of the theory. Now, so what is the evidence on the size of the economy-wide rebound effect? So what degree do energy efficiency improvements result in economy-wide reductions in energy use? It's important because the International Energy Agency and the IPCC, they expect energy efficiency to contribute significantly to reducing climate change, energy efficiency improvements. And if you look at the IEA projections, they expect improvements in energy intensity to cover about half the reduction in greenhouse gases. And an example is, this is their, it's a paper I published in 2017 in Climatic Change. I looked at how accurate the projections were in the previous World Energy Outlooks produced by the International Energy Agency. This uses what at the time was the most recent one, the 2016 one. This is energy intensity. So not actual efficient energy intensity. This is energy, the growth rate of energy intensity from 1990 to 2015, where it was some years, well, it was 1 year where energy intensity increased in 2010, but otherwise it decreased, but it had a variable rate. The average over this 1990 to 2015 period was this purple line here. And then they were saying in their projections, the current policies are only the policies that are already implemented by governments. This is what they expected to happen to energy intensity going forward. And new policies included Policies that governments, for example, had pledged as part of their Paris Treaty responses, but hadn't yet implemented, but we're going to. And that's the green curve of what they expected energy intensity to do. As you can see, this curve here, certainly in the early decades, is near the bottom of what we saw historically. So they expect energy intensity to fall at it as fast as it did in the years where it declined the fastest in the previous decade. So on average, a big increase in the rate of decline in energy intensity. And if you look at their scenarios for keeping global climate change to just 2 degrees, then they expect energy intensity to fall even more. But I didn't put that one into this graph. So in the IPCC, you'll see that in the 2014 fifth assessment report, the projections from the integrated assessment models show on average almost all models project energy intensity falling faster than it has done historically. So expecting this to energy intensity declines to do a lot, and the International Energy Agency attributes a lot of this to energy efficiency policies specifically. And this is Kenneth Gillingham again. So I liked his other article which had that macro price effect in. But here is a paper, short paper in Nature. I don't know if you can see right at the bottom there, it says Nature. The rebound effect is overplayed. Increasing energy efficiency brings emission savings. Claims that it backfires a distraction. Say Kenneth Gillingham and colleagues. So there was some talk that energy efficiency didn't actually save any energy, and Gillingham's coming back and said that's a distraction. We should ignore that. Okay, and really the rebound is probably not more than 50%. I think is what it says in this paper. So that is probably the received wisdom. Gillingham, of course, is at Yale, so people at Yale, a young guy, but one of the lead uprising environmental energy economists. Okay, on the other hand, we go back to 1865. The economist Jevons wrote a book called The Coal Question, which was about what was going to happen to coal resources in Britain. He was worried about coal actually running out. That was a bit misguided. Turns out there seems to be plenty of coal. But one thing he introduced was the idea that using fuel efficiency would actually result in saving coal and be one of the ways out of the limited stock of coal. And so the very contrary is the truth. Okay, so this is the famous quote that he thought that efficiency improvements were what that led, for example, improvements in early steam engines were very, very energy inefficient. They were only used in pumping water out of coal mines and similar tasks, stationary steam engines. As their efficiency improved, they could be used more extensively in those industries. They could be used for railways. And then later on, even for ships and factories. So the improvement in efficiency of steam engines led to their adoption in many, many more places. So and so there's a big increase in the use of steam engines. It wouldn't have been practical if they only remained about 1% efficient. The amount of coal that need to be transported would just be prohibitive. So that's why initially they were only in places where there was actually a coal resource on site. So this case, sometimes called Jevons paradox, also called backfire, is where rebound is more than 100%. So this idea is pretty old, goes back to 1865 at least, and there's been some revival of the idea in recent periods. So we have two contrasting views. One, people who say Jevons actually was right. This is still going on today. Then sort of mainstream view that it probably is a distraction and we shouldn't worry about. So what is the truth? So there's some theory about how big it is. So basically, Saunders showed that the more easier it is to substitute between energy and capital in production and energy and other inputs to production, basically the more flexibility you have in production, then the more more energy use or rebound in reaction to energy efficiency improvement. So basically more flexibility. If energy's very inflexibly combined with other inputs, then it's harder to adjust to that ratio, or you can't. Okay. Lemoine also showed that flexibility in consumption also is important. So this is between energy intensive consumption goods and less energy intensive consumption goods. If there's a higher elasticity substitution, it's easier to switch between energy intensive and less energy intensive consumption goods, then the rebound effect's going to be bigger as well. So more flexibility in production consumption makes it bigger. So it comes down to then, well, how much flexibility is there? And then Lemoine also shows that rebound will be particularly big for innovations in energy-intensive sectors, but it tends to decrease that in less energy-intensive sectors. So particularly in the energy industry, improvements in efficiency producing electricity, or in drilling for oil, like fracking, reducing the cost of oil. This has a big rebound, because those are energy intensive industries. They reduce the cost of energy for everyone in the economy, not just within their own industry. On the other hand, if there's there are efficiency improvements in other industries that reduce demand for energy, then that has a feed-on effect in the energy-intensive energy production sector by requiring less energy inputs there as well. So if a rebound's less than 100%, then that has a feed-on effect by reducing the demand for energy in energy production. But the reversive rebound is greater than 100%. So there's some more thoughts about what determines the level of rebound. Something important to be aware of is, so naively you might think energy efficiency, that's energy intensity. And a lot of papers, particularly ones coming out of China for some reason, assume energy efficiency improvements are energy intensity improvements. But actually, if we think about it this way, in the last lecture, right towards the end, I presented a framework for a constant elasticity of substitution production function using energy and labor or other inputs. And we measured the efficiency with which energy was used by this index of energy augmented technical change. This is an index of energy efficiency. So its effect on energy use, this is elasticity, the derivative of the log of energy with respect to the log of energy efficiency. We can break that down by just dividing energy use by GDP and expanding this expression out. So we have this derivative, the elasticity of energy intensity with respect to energy efficiency, and the elasticity of GDP, or output, with respect to energy efficiency. Now, this number here, the second term, we expect to be pretty small, actually, because if energy costs were, I don't know, 10% or 5% of the GDP of total costs, which I showed in the last lecture again, was where it was going to in developed economies in recent decades, then an improvement in energy efficiency can't have, according to standard economic theory at least, a big impact on output, because it's only in the margin, at least, it's only a small input to production. So this number, if the energy if energy cost shares like 10%, this might be quite small, 0.1 or somewhere in that area. So the rebound is big, and most of it actually is the adjustment to energy intensity to the energy efficiency improvement. And the implication is towards the upside. Okay. So it's, yeah, most of the effect is a bounce back in energy intensity rather than in GDP. So if you think this is energy efficiency, you miss most of the rebound. So don't do that. Don't think energy efficiency is energy intensity. So what do we see? if we look at historical evidence, some more analytical approaches, computational approaches, and econometric approaches. Okay, so there are a bunch of different ones out there. Historical evidence, this is the iron bridge at Coalbrookdale, England, where supposedly the Industrial Revolution started. Coalbrookdale is just behind the bridge. Those are where they smelted iron with coal for the first time. And they had so much iron they could build a whole bridge out of it, which seemed to be quite remarkable at the time. Okay, so this is a paper by a guy called Arthur van Bentham, and he basically is asking what is going on here. Why don't we see such, if energy efficiency improved so much, when we look at individual technologies, we don't really see that in the energy intensity numbers. So here he looked at energy consumption per capita on this axis and GDP per capita on this axis. He ends up with a bit of a curvilinear relationship, a bit of a S-shaped curve. I think he doesn't include biomass as one of the energy inputs. There's some other differences to the numbers that I used. But anyway, it's increasing as you have higher GDP per capita, you have higher energy use per capita. So the same basic story as I presented last week. So what we see here, these countries, Germany, United Kingdom, Spain, so forth, which are now developed economies, when they were poorer, their energy use, of course, was lower. And the same even for these countries up the top, the United States, Canada, Finland. When they were poorer, their energy intensity was lower. When we look at the upcoming countries, China here, Vietnam, Indonesia, or even India, they seem to be on roughly the same trajectory, or even more energy intensive for their level of income per capita than these developed economies were when they were at a similar low level of income. We see here's Taiwan, pretty much the same as is that South Korea? I'm not sure. Yeah, and there's anyway, Spain and Portugal are down here. They were relatively low energy intensity. Anyway, this jumble of countries here are pretty much all following a similar path, and maybe even the recent arrivals on the scene, or even maybe more energy intensive. So energy efficiency reduces energy use. Why is energy consumption per capita even higher in upcoming countries? And his argument is, well, the bundle of consumption services has shifted with improved energy efficiency to more energy intensive goods, like cars, which didn't exist, were used only by a few rich people when developed economies were at these low income levels. So there are lots of new energy services that are being used as energy efficiency improved. That suggests a big rebound effect in the long run. And this is a diagram from I showed you from last week. The energy intensity curves for all these countries, and comparing them to the dots were the energy intensity on this axis of all countries in 2010, and most of these curves, historical curves, are within that space of energy intensity in 2010. So energy intensity does decline as you get richer, but everyone seems to be on that same sort of path, and we don't see a lot higher efficiency. Okay, so I have a question. Can this higher energy use per GDP in countries like China also explain the fact they tend to be production countries as well for the richer Western world? Yeah, that's a point people often raise, that, and that might be part of the story why China is actually higher, that it's producing a lot of goods that use energy, which are then exported. Okay, well, they use a lot of those are labor-intensive goods, but of course they use power that's generated in China and so forth as well. That might be partly true, but remember, of course, that Britain historically exported goods to its colonies and all around the world, heavy goods. So in the early years, spreading the Industrial Revolution to other countries. So back then, it was It was an exporter of sort of embodied energy in the same way. The economies that are now developed economies and maybe are more importers. So might part of the story, but it doesn't seem to be. I don't think it's all of the story. And when we look at and Germany today is exporting a lot of energy intensive goods like cars to the rest of the world. The US exports planes because they're probably more technology intensive, I guess. US exports agricultural crops that are pretty energy intensive as well. But yeah, so it's not a simple picture there. I mean, there's some research that's been done on this, and getting to that issue of energy embodied in trade, uh, it's it's quite complicated. I'd recommend a paper by my colleague Astrid Kander, who's an economic historian, but a paper they published in Nature Climate Change in 2015 when they looked at that whole question of energy embodied in trade, different ways of looking at it. And depending on the way you look at it, you come up with different answers. But yeah, that's possibly part of the story, but I don't think all of it. Okay. Right. So that's the sort of historical evidence. Famous for supposedly trying to stop its colonies from getting industrialized, like India, and just grow cotton and send it to England, where grow cotton labor intensively, send it to England where it would be turned into cloths and re-exported. The same with the American colonies, where they use slaves to grow cotton and export it to Manchester, where the energy-intensive production took place. Saunders, 2008, Energy Economics. So here is this production function cropping up. So Saunders takes a different approach. We just looked at a historical approach. It's sort of just to use, if we know some of the parameters in this production relationship, and we have a very simple model of the economy, very, very simple model of the economy, but not really much simpler than the one that Nordhaus won his Nobel Prize for Economics of Climate Change for. The model doesn't even have energy in it. What can we say about the rebound effect? So this is output is here a function of capital, labor, and energy. And there's technological change improves the efficiency of energy use and efficiency of labor use. And sigma is the elasticity substitution, how easy it is to substitute energy for the other inputs. So over here. Oops. So he works out theoretically, assuming this is actually somewhat partial equilibrium. It assumes a constant price of energy and capital, but it allows the wage rate to change. And under those assumptions that he works out analytically, the rebound effect is this. This is the share of energy in costs, share of labor in costs, and then the elasticity substitution and some other parameters. So if you, whoops, wrong way. If you plug in elasticity substitution is 0.67, that's what we estimated in our paper on energy economic growth in Sweden over 2 centuries. So in the long run, we think actually it's not that small. It's there aren't very good substitute energy and other inputs, but about 2/3. And you assume energy costs are 0.1, 10% of total costs. Labor costs are nearer 60%. Capital share is about 30%. You plug all those numbers in here, you get the rebound is 79%. Okay, so he tends to argue for relatively large rebound based on those parameters. The Lemoyne's paper include a lot more detail in his model. He used, though, a very low average number for the elasticity of substitution between energy and other inputs. His average across sectors was 0.33. I think it's probably an underestimate. And he assumes that, as I mentioned earlier, that the elasticity supply of energy is infinite. So there's no macro price effect. Here comes a rebound of 38%, which is largely driven by this number here. Similar to Saunders, comes up with this number, largely driven by elasticity substitution. So it seems to be the biggest driver of the. There is enough to do a meta-analysis yet of these studies, but that seems the biggest driver. Okay, so those analytical approaches, again, it depends on the parameter estimates, and you can come up with lots of different numbers for what these parameter estimates are. There's not a good consensus. Oops, I moved forward too far. Yeah, so then there are computable general equilibrium models. These are much more general models of the economy, many sectors, and everything is adjustable. And Turner paper showed that for a UK simulation model of the economy, a computable general equilibrium model, the rebound could be from 322%, like huge backfire, down to minus 13%, negative rebound, depending on elasticity substitutions you put into the model. So these models tend not to be that empirically validated, so it's hard to know. The average of these results from these models is probably around 50% or so, but you can get other results depending on your assumptions you make. There's an interesting but unpublished paper by these guys, Rausch and Schwerin, who try to fit their general equilibrium model to the data better. They make some strong assumptions, though. One is that you choose your energy efficiency when you install capital based on the current prices of capital and energy. And so future changes in energy price don't have any effect on your end. Okay, so in the short, yeah, sorry, I'm probably saying that wrong. So yes, so when you choose your level of energy efficiency, you determine that based on the cost of energy and the cost of capital. Then the lower capital cost increases energy use over time. And so what they find, they translate this to energy efficiency improvement, but one increases energy use. So that's what they think the data show, and they come up with a very big rebound for the US using these assumptions in a more empirically calibrated model. But are these good assumptions? They might be good assumptions, they might not be, we don't really know. Finally, some econometric estimates out there. So Adutetu et al. Is probably the one that sounds the most plausible a priori in terms of the method. So they estimate energy efficiency in different countries using a so-called stochastic frontier model. And then they use those efficiency estimates in basically a demand model for energy. And they allow it to be dynamic. So the short run is different to the long run. On the other hand, their results find the short run rebound is very big, whereas in the long run, actually, it's negative. And this is somewhat determined by the dynamic setup of their model. The dynamics in the model are just that they lag the dependent variable. And that means that if energy use declines in the short run, it declines a bit in the short run, only 10%. In the long run, of the energy efficiency improvement, so there's a 1% energy efficiency improvement, energy use declines by 0.1%. In the long run, declines by more. That's sort of built into their model. And so they end up with a very big negative rebound in the long run because there have to be more energy. So I don't know. We don't know, is this number good, or is it the structure of their model that set that? Their model's got a lot of structure on it. Okay, so I've gone through theory and different approaches. The historical stuff hinted that the number might be big, but it's sort of anecdotal because it doesn't hold anything else constant. We're not seeing what happened to energy prices, for example. So we tried to find a new approach to estimate the rebound effect, trying to relax some of the assumptions in the previous literature and do things empirically. So we used a time series model called vector autoregression. I talked about that last week when I talked about the literature on energy in economic growth. People use vector autoregression models to see whether energy use changes caused economic growth or vice versa. Here we have a very similar model. We have energy use, output, and the price of energy. And we try to estimate the size of the economy-wide rebound effect using this model, but it's quite different in how we interpret the model to that literature on energy and growth range of causality. So as you'll recognize, Stefan is one of my collaborators, and also Alessio, I think, is on the call. And we got funding from the Australian Research Council for this project. And actually, our first paper from this was just published in Energy Economics. Okay, so the idea here is that we use this model and we see what happens. Is this just see? Okay, the idea is to see initially an energy efficiency improvement that reduces energy use. And then, because it's a dynamic time series model, over time, energy use might adjust or will adjust. It won't stay where it initially was in response to the energy efficiency shock. And I'll define what energy efficiency as a shock is later. So potentially, energy use changes by this amount. There's a big saving potentially initially, but then potentially it adjusts over time. So our approach depends on seeing what happens over time. And in this example, initially energy use is saved. There's a 1% reduction, but in the long run, actually energy use increases. So this is a backfire example. And you can do the same calculation of rebound as people did with energy saving. So these changes in energy use. So the actual here is like 0.4, the potential is -1, and so the rebound is greater than 1, greater than 100% in this example. Of course, that's extreme case, more likely to be not actually in energy use increase, which would be the curve is below that 0 line, then the rebound will be less than 100%. So we just depend on the data to tell us how much energy use adjusts in reaction to this initial change. Now, a problem with this might be that well, we're looking at what I think changes over time, and maybe there's adjustment immediately when energy efficiency improvement is adopted. So a new car comes out that's more energy efficient, but also heavier. So the question is how that affects the results. So this is the real world energy efficiency shock. We might not observe all of the shock. We might see a bit less of that shock because some of it happened immediately. So the adjustment over time is only part of the total thing. And here are so we tend to see less than the total change we assume. And if it's energy saving one, this will be the outcome. I'm assuming we can see the whole outcome. So in the energy saving case, there's a reduction in energy use in the long run, and there is an observed reduction in energy use initially. We're going back to here, we're then dividing the actual change by now the observed initial change. It turns out, if you think about that, this tends to, if the rebound is less than 100%, tends to bias it a little bit towards the 0 mark. On the other hand, if there's backfire, the rebound is greater than 100%, tends to bias it down a bit. But there are also other potential outcomes, and so that's not the only potential result. Was it? Sorry, biases away. Maybe Stefan can remind, biases away from 0 in both directions. In fact, sorry, not towards 0. Okay, so what's the kind of mod? So we took into account some of those things in our discussion that we don't necessarily see the whole effect. So we got the time series model. This X is energy use, GDP, and the price of energy. and it's a regression model with three equations, rests on the past values of these three variables, and then there's an error term here. Now, normally we think in standard econometrics, you think of the error term as being sort of the noise. You don't want sort of the waste. This is the real model. This is what you don't want, bad stuff. In the structural vector autoregression, which is kind of reversed, and the driver of change is these shocks to the model. So the structural var goes from, this is the model you actually initially estimate on the data, and then you transform it to this structural model. So in the structural model, we're thinking of these observed residuals in the regression are actually some shocks which are independent of each other and exogenous, and they can, through this matrix B, they can have effects on all the variables in the on the left-hand side, not just on the variable in their own equation. So it decomposes initial observed residuals into some sort of structural shocks. And the question is, how can we identify those? In our research, we identify them using something called independent component analysis, which I'll talk a little bit about. So our thinking here is we've got an empirical approach to estimating the rebound. That's true of the partial equilibrium econometric models. The analytical approach poses lots of structure and takes a few parameter values from other places, so it's not fully empirical. Same with CGE models, they impose a lot of structure and take parameters from here and there into their models. It's general equilibrium because we allow, in response to these shocks, all the variables, including the price of energy, to vary. And whereas this isn't the case in some of these other approaches, and we can plausibly say that these shocks are exogenous shocks. They're not explained by the variables or the lagged values of the variables that are in the model. Or you can debate that. So yeah, it depends how many control variables you put into your model. The traditional approach to the problem is that the parameters in this B matrix are greater than the parameters in the variance of the number of independent components of the variance of the reduced form residuals U. Going back, U is in this simple reduced form model. So now the structural model has more parameters, the same problem as in the traditional simultaneous equations model in econometrics. Traditional approach was to impose restrictions on B based on economic theory. There's also a sign restriction approach where you don't actually impose restrictions on the parameters themselves, but we want the parameters to either be negative or positive, and we accept only a subset of models which meet the theory imposed signs on the effects of these shocks on the model. So for example, if we claimed a model was a supply and demand model, that price shocks would reduce demand or increase supply and so forth. Okay, also we identify some as demand or supply shock. So the independent component analysis puts conditions on sort of on the distribution of eta of epsilon instead, rather than these theory-based restrictions. So it came from machine learning literature. This approach assume these shocks are independent and that they're not normally distributed. Normally we assume regression models are just normally distributed shocks, but that turns out that's often violated. So it's not that high in ones that are not normally distributed. So it needs that in order to be able to identify the model. And they find linear combinations of the reduced form residuals that are maximally independent using various criteria. One's called distance covariance. The maximum likelihood approach uses T distribution as an example, and there are some other ones as well. And this is used to estimate this matrix B. And there's a theorem that says that if this is true, then B is identifiable up to certain column permutations and signs. So is it negative or positive? So the approach you can use is to label shocks by the variable that they impact most. Distance covariance is a generalization of correlation. So it's famously, if two variables are the linear relationship, we can say they are highly correlated, correlation of 1 or 0.7 or 0.3 or very little, vice versa, -1 for highly correlated declining relationship between variables. But we can't say anything about all these other relationships here. Distance covariance is a generalization that allows to also say how correlated variables are in a nonlinear sense. Okay, there's an algorithm that does this, somewhat similar to the sign restriction algorithms that are used. I won't go into that. Nonlinear maximum, so the maximum likelihood one is another approach. Okay, let's look at the data. We use US monthly data. It's not the official GDP data, but some other people produce it using the official quarterly data and monthly series. We also have quarterly data for official government data. We have data on primary energy use monthly going back to 1973 from the US Energy Information Administration. So we're using US data because we've got monthly GDP, monthly energy use going back to 1973. Prices, some of those are monthly going back, some have some gaps here and there. We compute here just an average price of energy cost divided by energy use. We deseasonalize it because energy use is very seasonal, and the GDP data is already deseasonalized. Okay, so US data lets us estimate monthly data, high frequency. The reason we want to do that is we want to get near the beginning of an energy efficiency shock. This is the US monthly data. The energy since 92, energy use increased a bit and then sort of went flat. Energy intensity went down. So I don't show you the G here, I show you the ratio. And energy price went all over the place and largely dominated price of oil. Over quarterly periods, energy use was more of an increasing trend. Energy intensity still doing its downward thing, and the energy price drifting around with the oil price shocks here, and then the 2008 peak in the oil price and so forth. Okay, so data. So we estimate using we use a few different methods in the paper, 4 methods, and we estimate the parameters of this matrix. So remember, we've now sort of standardized the shocks, always have the same variance. So the first shock here has these effects on the 3 variables. This is the effect on the energy, this is the effect on GDP, this is the effect on the price of energy. And as the biggest effect on energy, we say this is the energy efficiency shock. The second shock has big effects on both GDP and the price of energy. But the third shock has a massive effect on the price of energy. So we label this energy price shock and this the GDP shock. Okay. So this is the response to these shocks. This is the energy efficiency shock up here. Initially, there's a big fall in energy use in response to this shock, but that disappears until we get back to pretty much no change in energy efficiency. So if we say this was energy efficiency shock, this means a rebound's around 100% here. This is a 90% confidence interval. Its effects on the GDP are pretty insignificant. They're a bit positive, which is what we'd expect, but not statistically significant. And the effect on energy price is negative, but again, not only for a short while, as it perhaps a little bit energy statistically significant. So this, according to economic theory, makes sense. It reduces energy use initially, increases the GDP because of the productivity improvement, though it's not very big. We don't expect, I said, we don't expect energy efficiency to have a big effect on the GDP. The price effect on price of energy is negative, but it's not that big either. But this GDP shock here has a big effect. You see this big positive effect on the GDP, somewhat smaller effect on energy use, and it increases demand for energy and increases the price of energy. Yeah, so that also makes sense according to economic theory. Finally, the price shock in the long run reduced energy use at least. Reduced the GDP and energy price shock, increased the price of energy, though not really in the long run. So according to economic, this all makes actually according to economic theory. This is an efficiency shock. There's some shock to the GDP, some productivity shock to the GDP, or population shock, and this is energy price shock. So yeah, rebound looks really big from this number here, and this looks at the rebound effect itself and confidence interval. It doesn't matter the method. After 6 years, it's around 1 or greater than 1. And as I said, if we miss the beginning, first of all, I said that wrong when I said it biases actually away from zero. So we missed the quarterly data shows initially a smaller effect, a smaller rebound than the monthly data, and the end a larger effect than the monthly data. So that's just because we don't observe things for a few months at the beginning, we miss part of the effect and actually behave similarly to what we predicted if we have low resolution data. But yeah, the rebound is big. There's the confidence interval around it across all these different methods and data sets. We also added more control variables, controlling for the mix of energy types. That obviously has an effect on energy use, structure of industries, industrial production versus other goods and services. That's those data series. Yeah, well, industrial production here is relative to the GDP actually was going down. So moved towards service industry, presumably. And energy quality got, well, it was sort of, energy quality is the mix of different energy types. It rises if we shift towards more expensive energy types. Actually, there was a shift towards less expensive energy types in this latter period. And including those variables really didn't change anything. After 6 years, according to all the methods, you end up with about 100% rebound. So we also have a paper co-authored with Anne Berner at University of Göttingen, and look at this for several European countries, UK, Italy, Germany, and France, as well as the US. We have shorter time series here. We end up with a similar result here. Initially there's a big shock, and then there's a bounce back towards zero, then all the way to zero, but a big bounce. This is the estimated rebound effect in the different countries over different time periods. Again, in the end, they all sort of include 100% in the confidence interval, which is the line there. So again, similar results to the US, at least in regard to this energy efficiency shock. And I went either afield, a co-authored paper with Mahbouba Jafari at University of Shiraz in Iran, using Iranian data. So here we have an oil exporting economy and middle income country, and quite a controlled economy in many ways. So the energy efficiency shock effect on energy, same kind of story going on here. So here we have the GDP shock increasing the GDP. Interesting thing here, it increases energy use by more than the GDP. And what we saw in Iran is energy intensity, energy per unit of GDP increased over time in Iran. So it's not surprising it affects energy use. So the growth of the economy has increased energy use a lot in Iran, whereas it tends to reduce it in the US economy. Here's the energy price shock. So these results, again, don't look that different to the US or Europe, even though it's quite a different setting. So that's interesting. So conclusions, again, bringing everything together. So there's no consensus here, but it does look like economy-wide rebound could be high. It's put it that way. Historical data looks like it's quite high. Debate in sort of analytical results. On our empirical method suggests that at least some component of energy efficiency results in a large rebound. But I don't think there is yet going to be a consensus on this question. If this is true, then sort of encouraging energy efficiency innovation is probably of limited value in mitigating climate change. And the IEA and IPCC, the expectation that there'll be more energy efficiency policies will result in more rapid reduction in energy intensity than has historically happened seems difficult to believe. Now, this is potentially the case when there are existing actually strong energy efficiency mandates. If we have an existing mandate to save energy that is a costly thing that stops people, that requires people to use less energy and have a smaller washing machine or whatever in order to save energy. And then you have an innovation that improves energy efficiency. Actually, in that situation, existence of existing costly binding efficiency mandates results in larger rebound than in our sort of purely free market theory analysis we had earlier. So this is a paper by Fullerton and Tarr that looks at sort of costly energy efficiency policies. On the other, whoops, sorry, I keep pressing the wrong button. Going to click on here, I get the wrong thing. Okay. So this is encouraging innovation in energy efficiency might not be that great. On the other hand, if you impose costly mandates that are not cost-reducing innovations that actually increase people's costs in order to use less energy, then they can have quite large effects because they might have a reverse rebound. So people get poorer and use less of the energy service because they were forced to use more costly equipment to save energy. So got to be careful with the implications of this rebound literature to make pronouncements about policy. Are you talking about encouraging energy efficiency innovation, or are you talking about imposing costly restrictions? I mean, I'm not saying they're necessarily bad things, but they impose costs rather than reduce people's costs. So that's quite a different kettle of fish, as we say in English. Really quite a different story. We're looking in this presentation at the rebound effect. Okay, so no oversell this result to all energy efficiency policies won't save energy. Some might save a lot, in fact, if they aren't of a sort of cost reducing type. Okay, so that is pretty much my presentation. Happy to take other questions.
Yeah, thank you very much, David.
Hopefully I didn't mangle the independent component analysis too much.
Well, that's a difficult thing to explain in a short lecture, I guess, right? Yes, so if nobody has a question, so I will ask one to give more time to think about
Yes, good
potential
idea.
questions. So what is your take on this remarkable similarity in the rebound effect across all of these countries? It's a really surprising result, right? That you find across all the European countries, across the US, and across Iran, basically a rebound of roughly 100%. What's your take on this?
Well, one interpretation is that yeah, rebound is big, and that's what we see in the historical data. If you sort of think of energy prices and not having moved dramatically in one direction or another, in the last week I said I didn't think the role of energy prices was that big in driving energy intensity. Yeah, we don't see a shift down in that energy curve. It's very consistent across countries um, over time. But countries get richer, they do reduce their energy intensity, but we don't see that curve shifting down with some sort of energy efficiency improvements lowering the curve. And that was very clear in my presentation last week, and also in the Van Bentham paper. So it's not surprising that we see energy efficiency improvement shock having no long run effects on energy use based on that data. Well, we do see countries reducing their energy use. Maybe I didn't bring this point across that well last time. Britain actually reduced its energy use or kept it constant for quite a long time. It looks atypical to other countries. The US in recent years, both those countries are ones which were very energy intensive earlier on. And we showed there was last week there was strong convergence in energy intensity, that the more energy intensive countries became less energy intensive and vice versa. Countries became more like each other. So some of those trends, I know you asked me about decoupling in the end, and I should last week, and I should have mentioned that. So we see, so once we sort of take out that sort of effect of being very energy intensive and what that does to your energy use trajectory over time, we see all the countries moving up that curve and that curve not shifting down. And so countries today having similar energy intensities to the for the countries in the past, probably not a big role for price of energy in driving the energy intensity. And so then, well, rebound must be big. And this says the same thing. On the other hand, we made lots and lots of assumptions in this analysis. So our energy efficiency shock is something that's independent of shocks to the GDP. And then don't know that that's true. So it may be only some type of energy specific shocks which aren't correlated with labor augmenting technical change or labor productivity shocks. There may be also energy efficiency shocks which are correlated with those GDP ones that don't have the same big rebound. We don't know. So we made a lot of strong assumptions, but it's interesting and it seems to match the just looking at those observations of countries moving over time and what's happened to them.
Okay, yeah. Oh, there is one question.
What could be the influence of the changing composition of GDP over time and or over the countries instead of the worldwide approach? So let's go back a bit. So one of the reasons why energy intensity may decline as countries get richer is because of a changing structure of GDP. They shift from towards the service sector. But I think that tends to be overstated, but there's some effects there. So that might be part of what you see. So that may lower energy intensity. And we did in our US, so we're just looking at the US, we're looking now with this structural vector autoregression model, one country at a time, rather than worldwide approach. And we controlled for this, shift towards the service sector. So this is the industrial production divided by the GDP. So it's industrial production divided by GDP. So it declined a lot around, actually, but these recessions, it went down and didn't recover. So there's been a shift towards services away from industry here. So we control for that variable here. In the 5-variable regression, that didn't change the results of the effect of this energy efficiency shock. Okay. So we're saying, yes, it could drive energy intensity potentially. It didn't, accounting for that didn't affect this energy efficiency shock. I'm trying to find what we see in the US here is a shock to the GDP, increases the GDP a lot, increases energy use less. Now, what is this shock? This may be labor productivity improvements, structural changes, whatever they are, population growth, because it's not per capita. Whatever they are, they increase the GDP more and increase energy use, and so these would result this GDP shock to reduction in energy intensity. Last week I said if that simple model was true, labor shocks wouldn't affect energy intensity, but the world may not be that simple model we had last time. So this suggests the GDP shocks are what lowering energy intensity over time. They're partly structural change, partly labor productivity, we don't know. And we see in Iran, by contrast, Iran and some other developing economies that started out quite less energy intensive and became more so over time. So they're converging from below. In Iran, this GDP shock increased the GDP by less than energy use, it seems. So they increased the energy intensity in Iran. And what's going on there probably is a shift towards a more energy intensive consumption bundle like transport and so forth with development of the economy. Possibly. So yeah, that's my answer on it's here and it probably affects energy intensity quite a lot, somewhat. But it doesn't change, the controlling for it doesn't change the result of this energy efficiency shock. Okay, that was a long answer maybe, but hopefully that answers the question.
Are there more? Yes, there is another one.
Is it possible to have a list of the papers used for your presentation? Not all, just a couple that are good. As an engineer, I found the subject very interesting and some results were not what I expected prior to having not researched before. Okay, so on my blog that's called Stochastic Trends, about a week after each lecture, Stefan is sending me the video from this, and I'm uploading the video on YouTube. And so far we have 2 up. And then I do a blog post on my blog, and I actually have links to the papers that the presentation is based on, because I thought people might want to follow up on that. Most of those would probably have blog posts on them as well. But I didn't link to the blog post because I thought I'm explaining them as lecture pretty much like I would explain in the blog post. So it's at a little bit less technical level than the actual full papers. So I didn't see the point of linking to the blog post, but I linked to the papers they give maybe a sort of full formal treatment. So yes, the blog will list after each video from one of these lectures the main papers that are involved. And most of those have both an official journal version and a working paper version. So I link usually to the REPEC, the Research Papers in Economics, which has a link for a published version, and it says other versions, it will have a link to the working paper version. So yeah, so that's an open access version.
Okay. Are there more comments or questions? Well, I have one last one.
Okay.
I'm interested in your answer on this. So imagine you are asked by the US government or some European or Australian government, what's your take on how to mitigate climate change? What's the role of energy efficiency in this? Given that you want to do an evidence-based decision and you look at this, at the literature and the results.
Well, I would say well, energy efficiency is it's a good thing as far as the welfare of consumers is concerned because they get more energy services out of a given energy input, so that's they're better off. But if you want to address climate change, you should have climate policies, and whether those are I would focus on well, pricing carbon. That's not popular in Australia, but we have some other we have a bidding for uh, low cost abatement bids. But anyway, so there's some pricing mechanisms here. But yes, climate policies that address the climate change directly. So pricing carbon, try to do that in an intelligent way that's politically acceptable. Um, there are some ways to do that which aren't simply a carbon price. I mean a carbon tax. And yeah, funding for research in low carbon energy, electricity storage, and so forth. These sort of components of because you probably won't have a carbon price that's high enough. You also need to probably subsidize research in some of those components of uh, the sort of low carbon energy storage. Okay, so it doesn't matter if we make solar power. Well, we make solar power cheaper, and people use more of it just as a rebound. But if we, yes, the general energy efficiency makes so we want to reduce carbon. So don't worry too much about this rebound effect or energy efficiency per se. To address the ways to get to low carbon. Yeah, that's it.
Okay. So yeah, thank you very much, David.
Okay,
The next lecture will be on April 23, so we have basically a large Easter break.
have a month to get it ready.
Any final words from your side, David?
No, thank you. Have a good break for Easter, and look forward to seeing you in April.
Okay. Bye bye.
All right. Thank you.